This video is part 1, chapter 11, describing data, confidence intervals, and correlation for PSY 222, research methods for the psychological sciences. In this chapter, what your authors are doing is, they're tackling a couple of different issues. They're trying to give you the big picture of what we do when we do hypothesis testing. In your semester project assignment, I've asked you to develop hypotheses and then test them using the database that you've been provided. And many of you are testing correlational hypotheses, as well as some between groups hypotheses. In the first part of the chapter, Shaughnessy et al. Are kind of giving you that bird's eye view of what are we trying to do when we do data analysis. And they describe it as a story because it does have a beginning and a middle and an end. Essentially, when we do data analysis, what we're going to try to do for our reader when they read our research reports is give them a full picture, a full story, as your authors put it, a narrative that explains what we found, explains possible interpretations, including those that go against our hypotheses or the perspective that we've chosen based on our review of the literature. And eventually you have to conclude your story by building an argument that justifies the conclusions that you've drawn, because that's how science works. Now, how we communicate that, the culture of psychology, is that we use APA style, which is from the American Psychological Association. We do use the style manual and the formatting and the structure that is expected of a research manuscript. In your semester project research report, you will be using that APA style in order to develop your research manuscript. We see this, and the we there is the department, we see this as a part of you kind of coming to understand the culture of expectations of doing science in psychology. When we do conference presentations and posters, there's also an expectation that we adhere to the APA formatting rules and expectations when we do so. Looping back around, this idea of developing a coherent narrative to describe the story of your study or your research program is also a part of that presentation ethic, where we're doing conference presentations of papers, we're doing posters describing research, and then you could also include there the publication of journal articles. We try to use a very common, agreed upon format for presenting these stories for a number of purposes, not the least of which is so that we communicate very clearly why we did the research we did, what kind of theoretical backdrop we are using to make the arguments we're making, a clear methodological process that is detailed enough such that another researcher could replicate what we've done, and then an explanation of both the data analyses and the conclusions that we've drawn that another researcher could read and understand and then perhaps argue about. Now, you've been learning a great deal. This week will be your final week working with the Pallant text and learning how to do SPSS work to generate descriptive statistics, to generate figures, to generate the results of hypothesis testing. Your authors call this computer-assisted data analysis. Researchers today, we typically use computers to do our statistical analyses. There was a time when you had to do all of the work by hand. It was laborious and very prone to error because doing large data sets even doing small data sets and doing statistical analyses and significance testing by hand is incredibly laborious, and it's very easy to make calculation errors. So it's a good thing that we have SPSS and other programs like it to help us do data analysis. There are a variety of programs available. SPSS is the most common one used in psychology, as it is designed for the social sciences. There are others, and there are also some newer programs that are out there available for free on the internet for doing basic data analyses and even more complex designs, such as one called R, that you can use in place of SPSS, although it has limitations in certain areas. When we use computer software to do the work, and you've been getting practice doing that, you still have to have a good understanding of what the statistics do, what the assumptions of the statistic are, so that you can fully explain to your reader what you've done and why. Remember how many times as you were walking through those instructions in Pallant, there was a test embedded in a test that you were running that checks to make sure that you have met the assumptions, or in other words, you've not violated the assumptions of a statistic you were using. It's important that you understand that backdrop as you are using these tools that make it so easy for you to just push a few buttons and get a test result. And that's why, we ask you, again, the we there is the department, we ask you to take a course like this to help you build a broader understanding of the context of data analysis before jumping ahead and just doing it. Shaughnessy et al. Described 3 basic stages of the data analysis process. First is, and this will mirror what you were learning as you did your Pallant homework this semester. The first stage is getting to know your data, being able to inspect it, to, I call it cleaning, where you're identifying any potential errors in the data, looking for outliers, looking for misscoring, and things like that. And it also may include generating some basic frequency data, including frequency distributions, just to make sure that you're acquainted with how the variables, when you do a frequency distribution, are they normally distributed? Are they skewed in their distribution, and so on? So that's the getting to know the data, and you'll recollect that that was the first couple of homeworks in your Pallant work this semester. Then we move on to summarizing, and that means generating descriptive statistics. And here what you're doing is, with quantitative variables, you're generating measures of central tendency, including means, and you're looking at standard deviations and other kinds of displays, so that you can get a sense of where in general is a set of data in terms of central tendency, and how spread out and what shape is the distribution. For qualitative or categorical data, we typically will present frequency information and percentages. We may present the mode as well. And then finally, the third stage is to test hypotheses. You want to confirm what the data show. And that's kind of the stage that you're at in your semester project now. And it's also the stage that you're finishing up with in your Pallant homework. So in the Pallant homework, if you've been struggling to figure out, well, why are we basically doing these 2 tracks in the bulk of the semester? Well, this chapter kind of pulls those threads together for you, where you've learned how to inspect your data, you've learned how to generate descriptive statistics, and now you're learning how to do inferential statistics, testing correlational hypotheses, testing between groups hypotheses. The claim that your authors are talking about here is your hypotheses. So the first stage, getting to know the data, and this should be review from what you learned in your Palette homework. You're going to look at the basic features of the data and clean things up if you need to. You're going to be looking for mistakes, missing values, impossible values, outliers. And again, this is something that you did in your Palette homework. You may want to do stem and leaf displays so that you can identify outliers and then make mindful decisions about what to do about those outliers. If you have genuine outliers that are so atypical of the group, they may constitute perhaps a subject on a survey inputting a mistake, inputting an error. And remember how I talked about that in one of my tutorials when we were looking at how many cigarettes had the smokers smoked in a week, and there was one person who reported a very, very high number, and you could make a guess that at least possibly that was a data entry error on the part of the participant. When you present descriptions, you can do so numerically, you can do it with pictures and graphs, and you can give verbal summaries. The stage 2 work that you do, and your authors focus on central tendency and variability. I have asked you in your semester project work to practice focusing, thinking about this as what kind of variable do I have? Is it quantitative or is it qualitative? And then generating the appropriate descriptive information for the type of variable you have. But I want to spend a little time just reviewing for you central tendency. The most common central tendency measure that we use to describe a set of scores that is quantitative. So think, for example, the questionnaire scale scores that you're using for things like perceived stress or optimism in your semester project or life satisfaction. Those all generate a total scale score, which you can describe for groups of subjects or for the whole sample with a mean. Notice that when we report means in our writing, we use a capital M and it is italicized. And we typically report the N. If it's for the full sample, you use a capital N and it is italicized. If it's a subset of the group, let's say you're reporting the means for males versus females, you're going to use a lowercase n for the subgroup. Median is another measure of central tendency. It's the midpoint of a distribution, so it's literally the middle score. If you order all the scores in the distribution and you identify the middle, if you have an odd number of scores, it's literally the middle score. If you have an even number, you average the middle two scores, and that's the median. Medians are used if using the mean is inappropriate. For instance, if you have data that's skewed, you may want to use alternate central tendency. Mode is the most common score in the distribution, and you may have more than one. Modes and medians and means, I tend, just when I'm getting ready to do my inferential statistics, I try to force myself to take the step of doing histograms so that I can look at the shape of the distribution, especially if I run the mode and I find out that there's more than one. I want to look at that distribution and kind of see what I'm dealing with in terms of the shape. Because if I have a non-normal distribution, if I have multiple modes, if I have a skewed distribution, it's going to determine not just what kind of inferential statistic I use, but also what kind of descriptive data I present to my reader. Now, variability with quantitative and qualitative data, we want to give our readers some kind of sense of the variability of the data. If you've got quantitative data and you present a mean, that mean really can't be interpreted without some way for your reader to understand how variable the scores for that variable are around that mean. So let's say I've got perceived stress scale mean scores, and I've reported the mean score for the full sample. And I know that possible scores can range from a very low score to a much higher score. Well, I need some way of summarizing for my reader just how spread out are the scores. Are they very tightly clustered around the mean, or are they very spread out around that mean? Now, a very simple measure of variability, which you would use if you were dealing only with just as a very almost crude way of describing variability, it's the difference between the highest and the lowest score. Sometimes what authors will do is they will report the lowest score in their sample for the particular variable and the highest score. They may not report the calculated range, but instead kind of give the picture of the high and low score, so the maximum and minimum. The standard deviation is the most common measure of variability used for quantitative data. So, for example, scores for a whole sample on the perceived stress scale in your semester project data set. We typically now use, instead of a lowercase s, we use a capital letters S and D for standard deviation. And again, notice when we write these, they are italicized. Pretty much all of your statistical symbols or letters are going to be italicized, even the Greek ones. The short version of defining a standard deviation excuse me, is sorry about that, little frog in my throat. The simplest definition of a standard deviation is the average distance difference between any score and its mean. So if you were calculating it by hand, basically you would subtract every score from the mean, and then you would create a standardized description of the difference. The variance is related to the standard deviation. Essentially, the variance is the squared standard deviation. Sometimes authors will report variance data if it's relevant to a specific statistic that they're using. And there are just some areas within the social sciences where it's more habitual to report the variance. In psychology, if we're going to report a mean, we almost always report the standard deviation with it. You may have noticed in your Pallant homework how whenever Pallant is reporting a test statistic, she also reports the mean and standard deviation for the variables that are involved in that analysis. Now, the formula for standard deviation is the sum of each score in the distribution minus the mean. You square those, that gets rid of the negative signs. You divide by the number of scores in the sample, subtract 1, and you end up with your standard deviation. Be thankful that we're not asking you to take a data set and calculate the standard deviation by hand. It's tedious. Another descriptive statistic that is sometimes reported is called the standard error of the mean. And this is a concept that we're just going to kind of throw out here for you. It's a concept that, or a statistic rather, that's used as a part of data analysis with certain kinds of tests that are run. Standard deviation, or the standard error of the mean, however, how it's defined is the standard deviation of sampling distributions of means. And it is described in your text as theoretical. The formula, which again, we're not going to have you do calculations of these, If you take the standard deviation, you divide it by the square root of n, provides you with the standard error of the mean. Some of our test statistics rely on the standard error as a part of their formulas. So your authors are putting it out here because of its involvement there. You may have noticed, if you really looked at the tables that are produced for the t-test, for the f-test in your Pallant homework, that some of those tables report standard error, or they have a column called error. That's what's going on there. These are measures of how well the sample mean is theoretically representative of a population mean. So you've collected a sample of, in our semester project data, we have something over 400 participants. That's a sample of Australian citizens of Melbourne. So the total population of Australian citizens of Melbourne, how well does my sample of 400 and whatever, how well does it represent? So this is statistically an estimate, and that's why your authors are calling it a theoretical sampling distribution. So how well does it estimate the population? I'll leave it up to the mathematicians and statisticians of the world to have a more complete understanding of it. For our purposes, understand that this is a statistic that is involved in many of the test statistics, the inferential statistics that are commonly used in psychology research. Generally, what you want is a small number. If you have a standard error of the mean, that suggests that there is something wonky, a totally official term. There's something wonky about your sample. So you may need to really restrict the degree to which you summarize. In your summaries, you generalize to the broader population without further verification and research. Your authors also describe something that is becoming more and more and more compulsory for researchers to report when they talk about their data, and that is effect size measures. Over the last, I would say, 15 years, so certainly long since I was trained. So when I was trained in graduate school, we were never asked to report effect size. There were a relatively small number of journals that were expecting effect size measures, and there were some specific techniques where it was expected that you report effect size. But generally speaking, it was not expected. I didn't start reading in journal articles a commonly reported effect size measures until the last decade. And part of that has come from just growing criticism of the over-reliance on significance tests, where we get, p is less than 0.05, we've got an effect. And, you have to put any kind of significance test result in its broader context before you interpret it. For example, there's a long-known correlation between premarital sex and it's a negative correlation between premarital sex and relationship satisfaction. So in sociological research, it's sometimes reported with these huge data sets. I mean, I'm talking 5 figures for the N, huge national databases, and they ask people hundreds of questions. And then sociologists will go in and sample some of that data to ask specific questions. Well, one of these tends to show a significant negative correlation between premarital sex and relationship satisfaction. And there's also the similar correlation, a positive correlation between that and between premarital sex and divorce. So you could jump to the conclusion that that having premarital sex or living together is going to make you hate your relationship and force you to get divorced. That would be a mistake, because when you really look at these correlations, yeah, the p-value is significant, but you've got in some cases 30, 40, 50,000 people in the sample, and the correlation is typically quite small and the effect size is tiny. So it's become more and more important for us as researchers to put our significance test results in the context of their meaningful effect size. So really, how big a mean difference did we find, or how big was the correlation in terms of effect size? And if it's really small, we have to be honest about that and say it really only explains this tiny proportion of the variance that we're looking at. So in the divorce data, for example, shacking up before you get married only accounts for a very tiny percentage of the variation in relationship satisfaction and ultimately relationship failure. So with that in mind, what does effect size do? These statistics provide us with information about how strong a relationship is, if we're talking about correlations, and how meaningful the difference between groups is on a dependent variable. These measures are designed, the example that I just gave you about the divorce data was purely an effect of sample size. If I have a giant sample, I can get a significant correlation result or between groups comparison result that looks wildly significant, but it really explains very little about variability on that particular variable. So effect size measures are not influenced by sample size. One of the common values that's reported is something called Cohen's d, and it's used when we're comparing sample means. And here what you're doing is, let's say you have a treatment group and a control group, you're going to divide the differences between those two means by the population, the estimated population standard deviation. And there's a lot of complicated statistical math going on in the background there. The formula, and I'm a visual kind of person for whatever reason, even though I'm not gifted in math. When I see the formula, you have the mean for first group, the mean for the second group, you're dividing it by your estimate of the sample or the population standard deviation, and that gets you an estimate of the strength of the relationship, and you're really factoring out the sample size to give you that value. When we interpret Cohen's d, and you've gotten some practice with this in your Pallant homework, Pallant gives you the same guidelines for Cohen's d. She also gives you some information about a different effect size measure called partial eta squared. You also may have noticed, and I find, frankly, the SPSS output with respect to effect size measures to be unnecessarily complicated and difficult to interpret. So it's understandable if you find it frustrating when this is the first time you're trying to use that information. But generally speaking, a Cohen's d of 0.2 is considered a small effect. And the way you should think of this is that 0.2 is kind of in the middle of a group of potential Ds. A medium effect, to declare something medium, you have to get a base of 5, of 0.5, and then a large effect is considered the lowest level. That would be a 0.8 for a large effect. The 0.2, that's a little looser. So you can also, if I get a D of 0.3, I still call it a small effect. If I get a D of 4, I still call it a small effect, because the guidelines are not precise. There's not an absolute cutoff, but there is an expectation. Some journals have really clear guidelines on what to report, and some areas of psychology have even more stringent requirements. Now, in the second stage of data analysis, just to review here, what are we doing in this second part? After we've cleaned up our data, now we're giving our reader a picture of who our participants are and how are they generally scoring on our variables of interest. So we report some measure of central tendency. If we're reporting quantitative data, we report means. If we're reporting qualitative data, we report frequencies and percentages. We also provide some kind of measure of dispersion. For quantitative data, what we're typically reporting is the standard deviation for each of the conditions of the variables. And then finally, we want to report effect size. Now, your authors are including the effect size as a descriptive. I typically don't report effect sizes as descriptive statistics. I report them right along with my inferential test results. But it is, from a statistical standpoint, it is a descriptive piece of information. And then in this second stage, you might also want to have pictorial summaries of the data if it's useful to your reader for understanding the story that you're telling about your data. For example, if it's useful to your reader, you might want to present a histogram. If it's useful to your reader and you have correlational data, you might want to present a scatter plot. It really depends on the context and the message that you need to send. You might also want to show line graphs or means plots if it's helpful for communicating an interaction effect, for example. But you eventually you need to decide how best to present summaries of the data. If pictures help, if they make things more clear, then you add them. If they're just redundant and they're not useful, I typically leave them out. And that concludes part 1 of our coverage of Chapter 11.